we've got two other operations that we want to look at in terms of functions. We have now looked at a couple of different shortcuts. We've done the derivative of constants. The derivative of constants is 0. We've done the derivative of constants times functions, and we have both sort of gathered the intuition and done the formal proof to say if I do a constant times a function, that's going to have me be that many times more or less of a height, which causes me to be that many times more or less of a rise, which causes me to be that many times more or less of the slope. So we've got this ability of saying, oh, I can just treat constants kind of like they're along for the ride and then do the derivative of the variable portion. And then we get the sum and difference. The sum and difference, again, we had the story of saying if I am adding or subtracting heights, I must be adding or subtracting rise, which means I'm adding or subtracting slope, which means I can do derivatives of things and then add or subtract. So that works out well as well. And then we had the product rule. The product rule is the first one that we just explored, where we don't just do the derivative of things and then multiply them together. We have to remember this interaction effect, where I do the derivative of one times the other as is, plus the derivative of the other times the first as is. So we don't always just do what's in front of our eyes. We do what we've explored through the story and then what we formalize through the limit definition. So before I go on, does anybody have any questions about the shortcuts we have explored so far? As a reminder, these are just shortcuts, right? I really, really, really hesitate to call these rules, because then people go off and they go like, oh, the derivative of things are this. And I say, why? And you say, because product rule. And I say, why product rule? And they say, because product rule and teacher told me. And I go, no, that's not derivatives at all. Like, teacher told me it's not derivatives. That's not logic. The real reason is because it comes from the what? What's the formal basis for derivatives? Was it? Not just slope. We got to formalize that language a little bit more. It's the approach of slopes, right? Which we formally define as the limit definition, right? So if we ever say, why are the derivatives this? The why is because of the limit definition. If I say, how did you do this? And you said, I did this by using the product shortcut, I'm gonna be like, that's totally fine. Product shortcut's a good how. Bad why, good how, right? Product shortcut is not the reason why things work. It's just a how I did things faster. We all feel pretty good on that? Okay, cool. Yeah, go ahead. Oh, yeah, this one should be there's a little typo there. Thank you for pointing that out. Yeah, plus or minus, good. Yeah, absolutely. If it's being subtracted, then it would be the subtraction of those rises, which would be the subtraction of those derivatives, because the subtraction of the approaches of the slopes. So this is a nice reminder that as we've gone through the course, we have started to evolve our language, right? I first got us very comfortable with saying derivatives are speed, right? Because I wanted you all to really latch onto something that was meaningful to you, that you could take into a context, and I was preparing you for the eventuality that we were going to relate integrals and derivatives through simple pictures, and that latter progression of being able to say, derivatives take me from position to speed, and from speed to change of speed or acceleration, and that integrals are an accumulation of acceleration over time, which affects my speed, and that an accumulation of speed over time affects my position. I've got this change that works with a story that you've all played with for years. Now, as we make that more formal, we go, okay, derivatives are not speed. Speed is one application of derivatives, right? And it's not slopes, although it is the slope of the tangent line. But when we actually dig into how do I get the tangent line, the formal definition emerges, and the formal definition for derivatives is that it's the approach of slopes, which means that if I'm ever asking for the formal definition, I need to write the limit of the difference quotient, right? The limit of the slope equation. All right, so now whenever I ask what a derivative is, I'm looking for you all to respond with it's the approach of slopes. Because then if you say, oh, I can use the approach of slopes to figure out speed, bingo, right? Speed is one application of that. Excellent. You're like, I could also use it to figure out slopes of tangent lines. I'm like, bingo, that's another application. You're like, oh, I could use it in this graphical context or in this function context. I'm going, yeah, you can. Run it, right? Because those are just applications of the formality. Okay, good. Let's talk about composition. Compositions, you all know back from algebra, is the ability to kind of take one equation and put it into another equation. I want to talk about it from, again, a story context. So I've got up here, I've got just a bit of a diagram. So what this is, I want you to think of it kind of like a mechanism, right? We'll start off with just, I've got this X wheel. This X wheel spins, right? Maybe think of it like me turning a bicycle, right? I've kind of got like a pedal. I'm turning that bicycle and I've got it connected to another wheel, another gear. We'll call that the U wheel. So now I've got like this ability, I turn the X wheel, it's got a belt that connects it to the U wheel, and so the U wheel turns as well. And I've got a ratio here. I've got a ratio here that says, since the X wheel is bigger, one turn of the X wheel is going to cause many turns of the U wheel. Give me a nod if we're following so far. So specifically, I've got this ratio of saying for every change in my X wheel, for every turn of my X wheel, I am going to cause 4 turns in my U wheel. Specifically, we could work out the algebra and determine that's because the diameter is 1/4 of that, right? So that means I've got 1/4 the circumference, which means it has to spin 4 times as much to be able to get as much spin as the X wheel. So I've got this ability of saying, okay, I'm going to turn the X wheel, the U wheel is going to spin 4 times because the U wheel is smaller. And I can even think of that as like running those moments, right? Running those time changes towards 0, because as I run those time intervals smaller and smaller, like 1 moment of change in the X wheel is still going to cause 4 times as much change in the U wheel, because that ratio doesn't change as I look at smaller and smaller moments of time passing. We all feel pretty good on where I'm getting this ratio right here from, saying du, the change in U in a moment, has to be 4 times the change in X for that moment, because whether I look at large intervals of time or moments of time, I've still got this connection through the belt. We all feel pretty good on that? Okay, cool. Now I've also got another wheel. We've got this Y wheel, and I've got a belt that's connecting them. The Y wheel I've made a little bit bigger. Specifically, I've made it twice as big as the U wheel. So the U wheel has to spin 2 times to cause the Y wheel to spin once. Now the question I have for all of you is, if I spin that X wheel 1 time, how many times does the Y wheel spin? We got twice. Do we all feel good on twice? We can run this through and we'll double check it. If I spin the X wheel once, I've spun the U wheel how many times? 4 times. And for every 2 times that the U wheel spins, the Y wheel spins once. So if it's spun 4 times, the Y wheel has spun 2 times. So we kind of see that rippling that's caused. And this should make sense. In fact, we could write this with ratios the way that we did in algebra, because it should make a lot of sense that the ratio of how much du and dx change multiplied by the ratio of how much dy and du change, that should be the ratio of how dy and dx change. In other words, that change ripples through multiplicatively. But there's a multiplicative flow for how the changes ripple. We all feel good on this story. I want this to come from a place of like, I see that moving, I see that happening. Because this has been dubbed the chain rule. But more specifically, it's just a chain shortcut. It's the idea of saying, if I have layers of change, then all I have to do is figure out how one layer changes, how another layer changes, and then I've got a multiplicative effect between them. We can think of this in a lot of story contexts. Let's imagine that I go to a storage facility and I want them to store a balloon for me, right? So they're going to charge me based on how much space I ask for. But if I all of a sudden like have that balloon spontaneously inflate itself, then like the balloon is getting bigger, and then I'm multiplying the size of that balloon by the rate for storage, and I've got more money that they're going to be asking me for at the end of it. I guess this has context. We can put this back into different scenarios. Just this idea of saying I can multiply ratios. So that's going to be our strategy. Our strategy is, if I have layers of change, I just need to identify the U wheel, I just need to identify the Y wheel, and I need to figure out how both of them are changing. so I can multiply the change. That's it. That's how we compose ripples of change. Let's look at an example. So we can see in this problem, I've got layers of change. Specifically, if I said, let's let x equal 10, somebody tell me what the first thing is that we would do with that value of 10. Would you only cube it? By 2 of those 10s, right? So that 10 is being used in many spaces. So the cubing, there's nothing special about the cubing being in front. In truth, that 10, if we plugged it into our calculator, would immediately substitute so that it was cubed, so that it was multiplied by 2, and then we would do the subtraction of that. So we've got all of those that would happen as that first layer. We could write that, let me kind of put that in some symbols so we can recognize that. If I'm talking about the inner layer of this process, the inner layer is, I'm plugging in that 10 for the x cubed, for the 2x, and the minus 3. So we all kind of see that that's that first layer of like what I would do. I would do that, get an answer, and then what would we do with that answer to get the final answer? We would square root it as that next layer. Now, what am I square rooting? I'll say y equals square root of what? Square root of u, right? Because I've already got that answer as u, and then I'm just going to use that answer from u and do a square root of it, right? Just like you would all if you're typing this in your calculator, right? You'd have one thing that you would have, and then we could possibly have many layers. Like maybe what we could do with that first x is we could just say, let's do the cube and then the plus 2x's, and then maybe the next layer is I add 3 to it, and then the next layer is I do a square root of all of that. Like we can make more layers if we wanted. I just want us to get this idea of layers. So do we all feel that this is one way of representing the layers that are captured in this function? So let's now ask ourselves how those layers change, right? I've got my u wheel identified, so if I change x, I change u. Let's look at that in terms of a derivative. The derivative of u would be what? 3x squared plus 2, right? Bring that 1 down and then decrease the power, right? You know, by the way, there's a parallel story that says 2x is a linear function. Linear functions have an approach of slope that is constant. That's why they're linear. And the slope for 2x would be 2, which is also another reason why this comes out as 2. What's the derivative of the negative 3? 0, because negative 3 is a constant. Constant graphs have no slope. Constants don't change. All of these stories work. It's still 0. What about derivative of y? Good. We can come up here. We can make this look in a structure to support the power rule. Bring that power down. Subtract 1 from the power, right? So that gets us 1/2 u to the negative 1/2. Now the chain rule says, take the change in one wheel, right, from one of those belts, multiplied by the change of the other wheel from the other one of those belts, and then I get that multiplicative change. So let's just grab the changes. I'm going to be doing dy over dx, which is the total thing, is equal to the change in the y wheel because of the u wheel, multiplied by the change of the u wheel because of the x wheel. So dy du is that. I just grab it and pull it in. Du dx is that. I grab it and I pull it in. And we're done. Well, kind of, sort of. If my boss said, I'd like you to go and figure out how the derivative of this thing is, and I came back and I'm like, I found that it has to do with u. The boss is looking at me like, what is u? The boss didn't give me a problem that had u's in it, did they? No, they just had it in x's. So I better translate it back to the boss's language so the boss knows what I'm talking about, right? But that's not calculus anymore. That's just us trying to make sure that it's recognizable. So I'm just going to grab u and I'm going to insert it so that it's back in terms of that language. And then from here, if you wanted to do a little simplification, make it look a little bit tidy, we absolutely could. I think that would come out as 3x squared plus 2 over 2 times the square root of x cubed plus 2x minus 3. But it should feel like something that makes some intuitive sense, right? That of course, if I want to have layers of change, that those layers of change affect each other multiplicatively, because if I change the first thing by double, then I would expect that double to ripple through and be double in some way for the final product. And that if I then made the second thing go down by a third, then the 2 times in the beginning is going to get compensated by the 1/3, and I'd probably be at 2/3 for the resulting thing. It's just changing multiplicatively. Yeah, question? Good? You're good. You want to try, Dan, the way you were talking, do you want to try setting this up with 3 layers? We can do it with 3 layers. Let's do it with 3 layers. I want to have some fun. Let's do it with 3 layers. We got time. So that's one way. We'll save this as an answer to see how we pull it in a moment. Let's make 3 layers. So I could make the first, what's a way that I could, I guess if I made this first layer be x cubed plus 2x. I'll just make it that, right? What do I do with the x's? I plug them in here. What's the next thing I would do with that u? Right, so again, let's imagine that I'm plugging in 10 for x. So I plugged it in, I got 10 cubed, and then I added 2 times of 10, and I got an answer in my calculator. Let's keep solving that. What's the next thing I do? Was it? I don't think this tells me. Oh, there we go. It does tell me to subtract 3. I thought it said add. You're right. Subtract 3. So let's we need another layer w. I find that to be a little bit ironic in the name of w, because the first thing I used was a u, and then I'm adding one more layer, so I should double my u. And you got to find little moments for whimsy in the class, right? And then after that, what would we do with that w? We would do the square root of it. Okay, so we could say that that's going to be y, our final product. That'd be the square root of w. Again, we know that this should be layer of change times layer of change times layer of change, right? Like we're just looking at this in terms of layer, layer, layer. So let's say that we're going to look at, I guess I could write this simply as saying the change overall is going to be the change in the first thing. Oh no, that we start to notice that sometimes the notation's a little bit wonky if we're talking about y prime. Y prime based on what? Based on x, based on w, based on u. This is why we use that sparingly and sometimes prefer the Leibniz notation of saying dy over dx is equal to dy as dw changed times dw as du changed times du as dx changed. And again, we can see that those du's would have canceled, the dw's would have canceled, and I've got that same ratio relationship we would have expected. So change in y as a result of change in w, that would be where we had to make this into a fractional exponent. That means that the derivative of y based on a change in w would be 1/2 w to the negative 1/2. So I can write that in. dw du, what would be the derivative of u minus 3? How come 1? Are we looking at it through power rule? Remember, we could also look at it because u minus 3 would graph as a line with a slope of with confidence, y'all, slope of 1, right? So the derivative is 1. There you go. dw based on a change in u is 1. And then this one is going to follow that power rule. Oh, so now we start to recognize that like what we have here is starting to shape up just like our original solution But then again, I've got to replace w in terms of u's. But my boss still won't understand u's. I need to make u's in terms of x's. And we're back to where we were before we started simplifying in the last example. So again, I like this very much of being able to have kind of the mise en place off to the side to be able to write the derivative, the chain rule in a way that makes sense, that we can see how it will ripple through the pattern. The layers are not important, but I do find that analogy of the X wheel quite helpful, because you want to make sure that all of your X's are captured in that first relationship here, right? There should be no X's that appear here or here, ever, because then that means I've got multiple belts and a whole different mechanism that I've built, right? All of the X's should be able to be captured in the first thing so that it changes the U wheel. And then I should have X not connected to anything else. It should then be U is the only thing I need to turn the Y wheel. Yeah. Like that? Excellent. Wow. Oh, that's so good. I love those moments when I feel good at my job. So if I do have something that is as a fraction, the question is, again, can I think of this in terms of layers? So this is Gabe's question. Gabe gets to tell me what layers. You see. So the first layer is 1. Okay, so then I take that U wheel, and that U wheel is changed based on the 1. Okay, then what? Well, I thought the X wheel moved the U wheel. So we need all the X's to be in the first capturing. So what X's do you see here? X squared. So now if I change X, all of the X's are captured there. Do we want to make it a little more detailed? Like, could we make it X squared plus 1? Because otherwise we're going to have a layer of just plus 1, and that's not really going to do much for slopes. We can help kind of combine, right? So now I've got, I plug in, I change my denominator. And then what do we do with the denominator? Like, what do I do if the denominator comes out to be 50? What do I do with that 50? We do 1 divided by 50. What is that operation? We can think of it as setting up as a fraction. Like, okay, so we've got y like that. But how do I do that derivative? We can make it into the power of -1, right? So we're also recognizing that even from the very beginning, we could have looked at this as that whole thing to the -1st power, right? And then again, it makes it very apparent those layers, right? I've got an inside of X squared plus 1. I've got a next thing I do, which is raise it to the -1st power. But this is fine too. So now if I want to find the derivatives, let's go through this layer by layer. So the first thing we need is we need that du based on dx. Our rule gives us 2x. I need dy based on du. That would be -1 comes down, the u gets decreased to a -2 power. In fact, at this point, if you wanted, you can start to organize off on the side that we know we're going to substitute everything back in terms of x. So you could even off to the side start making this be something like -1 times, what is u? Oh, it's up here. X squared plus 1 to -7. Are we all comfortable with me kind of writing that off as part of my mise en place instead of the simplifying? Again, you find you do you, right? None of this is required. You just choose whatever way you'd like to organize your thoughts. But now off to the side, I can say, okay, if I want to figure out dy as it changes on dx, that's going to be the derivative dy per du. times du per dx, which is -1 x squared plus 1 the negative second times 2x. It's at this point we start to see a little bit of preview for how I'm going to be solving these chain rules faster and how you all can work up to solving these chain rules faster, because we start to recognize there's a bit of a pattern, that the pattern is in this part here, you're really just doing the derivative of that -1 exponent, right? The -1 came down, you decrease the -1 to a -2, everything in the center stayed the same. Then we did the derivative of the first layer, right? The derivative of the inside only. So if you want in real time, when you start getting comfortable with this, you can be like, oh, okay, like I just need to do the derivative of the outermost operation as if the inside didn't change, the derivative of the next layer as if its inside didn't change, and then you continue that pattern until you've exhausted all layers. But I've seen a lot of people get tripped up with this for the first couple times that they do it on tests, because they start trying to do too many derivatives in one layer as opposed to doing them each as their own. So my strong recommendation would be go ahead and do the mise en place organization through this test, right? Like we got a test that's going to be in a few weeks. Like do this. It will help make sure you get full credit. After you start doing enough of these problems that you're like, this is exhausting, I know how it's going to look, then start experimenting with maybe making it a little bit faster. But like there's nothing worse than running too quickly and tripping, right? That just makes the fall hurt much more. Also notice, by the way, that this came out as a derivative with subtraction and a squared denominator. On top of that, we did the derivative of something containing division. Oh, well, that gives me insight. We could maybe come up with a shortcut that deals just with division problems, and we could find that shortcut by just considering it as if it was layers with negative exponents. Let's start taking a look at what that looks like. So I've got this one listed out in terms of text, just for the ease of time. Again, all of this is provided for you in the guided notes. So if you'd like, you're more than welcome to kind of just follow along with me up on the screen and then go back to the guided notes to supplement your notes later, because I really just want to make sure that we all have an understanding of where this comes from and why. So are we all on board with, if I have some function that is the division of two others, that I can rewrite that in terms of the numerator times the denominator to a negative first power? Now we've got to be careful here with your notation, right? This -1 power is an exponent. It's talking about division to a y value, right? To a thing coming out of a function, a number. This is not the same thing as a -1 used to talk about inverse functions, right? So we just want to be very careful in our parentheses that this -1 here is referring to the division, and that there will be other times we explore the derivatives of inverses. This is not that, okay? This is just division. So I've just got a little bit of structure here, right? We did the derivative of f of x. That'd be the derivative of the fraction, which is the derivative of the numerator times the denominator to the negative first power. I'm just kind of writing out blatantly everything we just talked about. So now we have two rules at play. We have multiplication, that's the product rule, and we have layers for one of the pieces of that multiplication. That's the chain rule. So we're going to have to account for both. What's the bigger structure? Like what's the, I would say, the later operation? Do I have chain rule within a product or a product within a layer of chain rule? Chain rule within a product, right? I do chain rule and then I use that as part of a product, right? I've kind of got this idea of saying chain rule is a subcomponent of the product that is the whole thing. So we're going to make sure that we do the division of the product. And then if I need to find the derivative of the chain rule, that's a piece of the product. So we'll first do that product rule, right? Because we're trying to set up that big structure. So I do the derivative of the first thing. The derivative of the first thing is just that g, that numerator, times the other thing left alone, right? Derivative of g times the other thing left alone, plus the g left alone times the derivative of the other thing. We all good? This is representing the product rule that we all agreed on. Okay. In order to do the derivative of that other thing, I've got to think of it in terms of chain rule. So off to the side here, we could say that this 1 over h is h to the negative first power. But again, this can start to look like inverse notation. So it's a big like recommendation here that if you're ever trying to really be careful, put the h in parentheses to show like it's that result of h that I'm then doing a -1 on. I'm not doing the -1 to the h, I'm doing the -1 to the result of what comes out of h. Well, if I do the derivative of both of these, this one over here is going to be where I have that -1 layer, so that -1 comes down. The inside stays the same, and I decrease it to a -2. That's the derivative of that first operation, that outermost layer, right? That latermost wheel. And then I do the derivative of the inside, which would be for the earlier wheel. That would be the derivative of h. A little bit of that simplification causes this to be -h prime over h squared, which means that should actually be a negative. Are we all feeling good on where I got that piece from? So we do a little bit of simplification. We've got that g prime over h being added to the g times that -h prime over h squared. Make those common denominators. Now I've got g prime times h over h squared minus g times h prime over h squared. Push them together, and now I've got sort of my summary formula. My summary formula is that if I do the derivative of some kind of fraction of functions, that's going to be g prime times h minus h prime times g all over h squared. Now, I like to remember this with a little bit of a limerick. Some people have different limericks. Here's my limerick. Low d high minus high d low all over denominator squared we go. Right, so let's see where that's coming. Low d high, right? So I've got low is h. D high is the derivative of the high. So I've got h derivative of the high. Low d high minus high d low all over denominator squared we go. So we can use this as a way of being able to remember how to do the derivative of quotients. Let's do an example. So here I have a function that is determined as a derivative of other functions. Again, big fan of this whole like mise en place idea. Let's get everything organized off to the side. We know we're going to have the derivatives of lots of things come into play. We know we're going to have the originals of lots of things come into play. Let's organize it all off to the side. So here, let's give it some labels. Let's say that I've got g on the top, x squared plus 3. Let's call h of x the thing on the denominator, x plus 5. And I know I'm going to need their derivatives. So I've got g prime would be 2x, and h prime of x would be, what would it be again? 1, right? It's got slope of 1, power rule, give me 1, it's 1. Once we've got these off to the side, we can just let our limerick carry us, right? So our limerick is low d high minus high d low, all over denominator squared we go. So we can go ahead and let this flow on through. Low would be the h, low times d high, minus high d low, derivative of the low, all over denominator squared we go. This is our derivative. If you want, we can do a little simplification to make it look pretty, but we're done now. Just because I enjoy having a nice, well-rounded story, let's again remind ourselves and imagine trying to solve the limit of the difference quotient by plugging in this big thing. Right? We plugged in f of b's and f of a's into this whole big fraction and tried to do a bunch of simplification so that it factored out and was able to cancel with the b minus a on the denominator. Like, oh my golly, pages and pages and pages of work. Even if you did the x plus h version, right? You plug in x plus h into that whole fraction every place that you see an input, and you try to do some subtraction and some simplification, pages of work. But because we allowed ourselves the ability to say, let's explore these shortcuts from the limit definition with general functions, now we're allowed to use all of that insight for every problem here on out, and we don't have to use the limit definition unless a specific test question asks you to show me that you understand it, right? But that this is a shortcut that in 3 lines of work, in fact, in 1 line of work, I got the same derivative that I would have gotten with the difference quotient. The other 2 lines of work were me just making the algebra look pretty, right? But this was the derivative. There it is. That was the derivative. We could have stopped there. And in fact, on the tests, you will be asked to show me that you have that technique, and sometimes you'll be given permission not to simplify. So that first box, you do the limerick, you mix and match as needed, you box it, you're done. That's the derivative.